Hello everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we looked at decision trees and how they can be trained when you are dealing with a regression problem, that is you want to predict the value of a continuous variable. However, the formulation that we derived was only true if we already knew the architecture of the tree, meaning that where the branchings are taking place, what is the decision node at every level and what are the leaf nodes. However, we need to have an algorithm which will tell us the architecture or the structure of a decision tree. Today we will learn how that can be determined. So let us go ahead and get started. So the topic for today is again decision trees in machine learning. And right now we are dealing with applications to regression problems, wherein you are trying to predict the value of a continuous variable. And what we had written in the previous class is that the prediction, right, of y, which is the target variable, as a function of the feature vector x, this is just a sum over all the regions, right. You have ck times an indicator function x belongs to rk, right, and this goes from k equals 1 to m. So this m is the total number of regions, right, into which the feature space has been partitioned. K is an index for the regions and this I, as you know, is a binary indicator function which tells you whether the point x lies in the region Rk or not, right. The main thing that was to be done is to find out the optimal values of these Ck, right, which are the values assigned to every region, and we said that these Ck hat, right, can be obtained by minimizing the sum of squared errors, and it was very simply shown to be essentially the average value of the target variable in that region, right. So you have yi times I xi belongs to rk divided by the number of points in that region, which is simply sum I going from 1 to n, the indicator function of xi belonging to rk, right. So this is very simply the average of all the yi which lie in that region. Okay, so that is the optimal value of the coefficient Ck hat which are assigned to every region, and this formula, as you can see, is applicable only if we know what each region Rk is, right. So this formula is applicable if the regions Rk are known a priori. However, that may not be true, right. We may not know what architecture the tree should adopt, and therefore we have to use an algorithm called recursive binary splitting. So this is a greedy algorithm which tries to maximize the accuracy of the prediction at every stage. So it is recursive because it has to be done again and again and again as you keep on branching the tree. It is binary because at every point you only branch the tree into 2. So that is why it is called recursive binary splitting. Alright, so how do you do this splitting? There is a sequence of steps that you need to follow, and I will discuss those steps now. In the first step, the best splitting feature J is determined by iterating over all the features and finding the optimal combination of the feature j and cut point s. Okay. So, what is a cut point? The cut point is the value of the feature j, right, to the left of which you will go to one region and to the right of which you will go to another region. So, that is the meaning of a cut point, right. So, the cut point divides the feature space. So, the cut point S divides the feature space into two regions. And these are, let us say R1, right, that is a function of the feature number j and the cut point S. So, that is defined as all the data points x where xj is less than s, where the jth feature has value less than the cut point s. And the second region is R2, right, which is the right partition or the right region. Again, it depends on the feature cut point combination. So, this is all the data points x such that the jth feature is greater than or equal to s, right. So, these are the two regions into which your feature space has been divided by the combination of the feature j and the cut point s. So, that is what is happening here. And now, how do you find the optimal value of j and s, right, that is what we need to do here. We need to find the optimal combination of j and s. So, that is done by minimizing, right, the error that is being made in the prediction of the values in the two different regions as quantified by the sum of squared errors. So, the optimal value of j and s are given as the output of an optimization problem. So, it is basically the argument at the minimum of this function, right, the error made in predicting the values in the left node. So, xi belongs to R1, which is itself a function of j and s. The difference between yi minus the average value of the region R1, because you know that in a decision tree the value you assign to the prediction is basically the average value in that region, right. So, that is the error made in the left partition of the tree, and in the right partition of the tree you look at all the points xi which belong to the second region, right, R2 as a function of js, and minimize the error between the true value and the predicted value, which is just the average value of the points in the second region, right. So, that is the total error, and you are trying to find the optimal values of j and s. So, the arguments, right, you are trying to find are j and s. So, I hope this makes sense, and this as per our notation is the mean or average response in region R1, and y bar R2 is the mean response in region R2. Okay. So, once you do this you will be able to find the optimal feature cut point combination. So, this procedure is done once, and of course, it has to be repeated on and on and on till you keep on growing the tree. So, the process to find the next feature cut point combination is repeated, and the tree is grown till the desired loss function value. So, for example SSE or MSE, the sum of squared errors or the mean squared error is reached. Okay. So, that is how you keep on branching the tree and keep on going down again and again and again. However, there is, right, a problem, right, with this, because what you will keep on doing is you will keep on branching the trees more and more and more to the point that it will lead to overfitting, right. So, this may lead to overfitting, as the number of branches can be kept on increasing till each point is its own region. So, if each point is its own region, what will be the sum of squared errors? It will be 0, because the mean response in each region will be the value of the target variable itself, and therefore, this whole loss function will be 0. So, the good thing here, right, is you will get a mean squared error of 0, but the bad thing is that your tree has completely memorized the entire data set, right. It has not learnt anything, not learnt which points are similar, which should be grouped, but rather every point is its own region, and that is clearly a case of overfitting. So, if you try to test the model, right, on unseen data, the model will perform miserably, right. So, that is clearly a problem. So, how do you solve this problem, right? How do you make sure that overfitting does not happen? So, a potential solution is to add new regions only when the reduction in the loss function. So, only when the reduction in the sum of squared errors, let us say, is larger than a certain threshold. Right. Only when your SSE decreases by a significant amount will you try to grow the tree by adding that feature cut point combination, right. However, this is a short sighted solution. This solution is short sighted, because later, right, you may be able to grow the tree and reduce the SSE much more, right. So, because one could miss out on regions that are more optimal for the model, right, for the loss function to reduce, but they appear later in the tree. So, this is a drawback of this proposed solution. So, what people eventually end up doing is they follow a regularization strategy. So, again regularization is making a comeback. If you remember, regularization was something that we looked at when we saw ridge regression and lasso, wherein you wanted the model to not overfit. So, you had a penalty from any of the features becoming too large. So, that is something similar that we will do here. So, instead one uses an approach via regularization, which is called cost complexity pruning or weakest link pruning. Okay. So what is happening here when you do cost complexity pruning or weakest link pruning? So the word pruning by itself you may have come across, right, when you are talking about a bush or a tree or a weed, when you are trying to cut off the branches, right. So that is exactly what we will be doing here. We will prevent the tree from growing overly, right, from becoming overly complex. So and that is essentially pruning of the tree, because you get rid of some branches. So this pruning is done to limit the size of the tree and thus prevent overfitting. Okay, so that is what we want to do here. We want to prevent overfitting, so we limit the size of the tree. Okay. Now we have to define mathematically what is meant by the size of the tree. The size of the tree, which is also called complexity, is defined as follows. So the complexity of a tree is essentially the number of terminal or leaf nodes in a decision tree. So thus to obtain the optimal decision tree, right, one grows the tree fully or to whatever point we want, to the desired extent, and then comes back and regularizes it. Okay, so how is this done? So we have to write down the objective function with the regularization term. So regularization, as you remember, is a penalty, right, to prevent the model from becoming too complex. So what you do is you minimize, right, the error between your predicted and the actual values, of course, right. So you have to sum over all the decision nodes, and then you have to look at all the points in those decision nodes or regions, right. The difference between the actual value and the predicted value, which is the mean of the values in that region, right, plus a penalty term, right. So the penalty is the number of nodes in the tree, and that number of terminal nodes in the tree, and that is what we are denoting by this t, right, lowercase t, which is a function of the tree that is being considered, which is capital T. Okay. So you are minimizing this, right, over all possible sub trees that can be constructed from your original tree, right. So we grow the tree to the desired extent and we obtain a tree, let us say T naught, and then we choose a subset of these trees, right, which are sub trees, and then we see which of those sub trees is leading to better generalization. Okay. So this lowercase t is a function of capital T. This is basically the number of terminal nodes in tree capital T, and it is also called the complexity of the tree. Okay. And alpha, as you all very well know, that is essentially the regularization parameter. And you will remember it from lasso and ridge regression. Essentially we want to prevent overfitting by making by preventing the tree from becoming way too complex, right. And this as you know is basically the sum of the loss functions, right, summed over all terminal nodes. okay. And the important point to note here is that these T's, right. So, T is essentially a subtree of the original tree T naught, right. So, you can denote it as T is a subtree of the original tree T naught, and T naught is the base tree obtained without regularization. So, formally T naught is the base tree obtained without regularization. Okay. Now you can ask a few more questions, right. How do you find the value of alpha, right, how much do you penalize the complexity of the tree, and the answer again is that alpha is a hyperparameter, right. It has to be set before the training of the tree happens, and therefore it can be determined by some form of cross validation. If you remembered, in the previous lectures we looked at grid search CV, randomized search CV, right. These are all cross validation tools to find out the optimal values of the hyperparameters. Okay. So, this is essentially our discussion of how decision trees work for regression problems and how you can prevent overfitting by using the cost complexity pruning or weakest link pruning approach, which essentially looks at subtrees and tries to add a penalty from the tree from becoming too complex, and by complexity we means the number of regions essentially, right, the number of terminal nodes in the tree. Alright. So, now that we have completed the discussion of classification problems with decision trees, we will now look at the training of decision trees for classification problems. So, the next topic is training decision trees for classification tasks. Okay. So, since we have already looked at regression, the logical progression now is to look at classification, right. So, as you remember, here you cannot use the sum of squared errors loss function, right. You have to use a different loss function, and if you remember from one of our previous lectures, typically it is the binary cross entropy loss, right, or log loss for binary classification. So, for binary classification, which is what we will look at, the loss function is either called the log loss or the binary cross entropy loss. If you remember, this function is essentially a sum over all the points with the cross entropy, right, which is essentially the entropy of the true value, right, with the log, sorry, the true value of the class multiplied by the log of the predicted probability, right. So, yi log probability of yi being 1 plus 1 minus yi times the log of 1 minus probability of yi equals 1, right. So, this is the log loss function, and essentially this is trying to find, right, what is the error made in predicting yi equals 1, right, and yi equals 0. So, yi equals 0 typically we are calling it the first class, right, and yi equals 1 is the second class, right. Remember, we are doing binary classification, so there are two classes here. Alright. So, now let us go ahead and see how this problem can be simplified. Okay. So, if you remember one of the previous simplifications that we had done for this kind of a loss function, we had written it as minus 1 over n I going from 1 to n yi log of pi hat. So, pi hat is the predicted probability plus 1 minus yi log of 1 minus pi hat, right. So, this is what you can write it, and you can now write it as a sum over classes. So, that is minus 1 over n sum c going from 1 to 2, the indicator function of yi being equal to the class that we are considering times the log of the probability of that particular class, right. So, if you look carefully, this term is this term here, and then the yi here, right, and 1 minus yi, they are basically the indicator functions, right, whether you are belonging to a particular class or not. So, instead of binary classification, if you had a multi-class classification problem, so for a multi-class classification problem, you know that you will use the multinomial cross entropy loss, right. So, the loss function, right, can be the multinomial cross entropy loss. And that is essentially L equals minus 1 over n average over all the data points, you sum over all the points and then you sum over all the classes. Let us say there are d classes here. So, the indicator function of the point actually belonging to class C times the log of the probability that we had predicted that point to be of class C. Okay. So, this is the index for the classes, and this d here is the total number of classes. Okay. So, I hope this makes sense to you, and now again like regression, right, what happened in regression, every region predicted a single value, and that is what will happen here, every region of the decision tree will predict a certain class. So, akin to the regression case where every region predicted a single value, here each terminal node will predict a single class. And thus the loss function can be written as a sum over each terminal node, right, because every terminal node will predict a single class. We can just write the loss function as a sum over the regions, right. So, let the regions be Rk as we have done before, and the predicted probability of class C in region K be denoted as PCK hat, right. So, C denotes the class that we are considering and K denotes the region that we are considering. Okay. So, then this log loss function, right, will essentially be minus 1 over n sum k equals 1 to m. So, we are considering m regions, and then we should look at the points which belong to that region, then we should sum over all the classes. So, the indicator function first has to appear, right, whether the point is actually class C multiplied by the log of the probability, right, that we had predicted for that region, right, to have class C. Okay. So, this is what is the loss function that should be considered. Okay. Now, if you recall in regression, that is all we had to do, we wrote the loss function and then we could minimize it to find the optimal value of the CK hats. However, there is one more thing which should be considered here, and that is that all these probabilities, right, typically they need to sum to 1, right. So, there is a constraint, these probabilities are not independent, and the constraint is that if you summed over all the classes C equal to 1 to D in a particular node, right, p hat k c, this should obviously be equal to 1, because that is the total probability of finding any of the D classes, and this you can write as sum C equals 1 to D p hat k c minus 1 equals 0. Okay. So that is the constraint that we have, and now we can try to minimize the loss function. Okay. Now I am not sure if you have done previously things like constrained optimization, but that is done through a method known as the method of Lagrange multipliers. So for incorporating the constraint, we use the method of Lagrange multipliers. Okay. And this is a very valuable method for someone to know, right, whenever you have to do a constrained optimization problem. Alright, so what we will do now is we will end this class here, because there is quite some amount of derivation left. So in the next class we will take up the Lagrange multiplier method to optimize the cross entropy loss function and find the optimal values of the predicted probabilities p k c hat, and you will see that similar to the regression problem where C k hats, they were the average values of the data points, right, in a particular region. Here in classification, the optimal probabilities p c k hat will simply be equal to the fraction of points belonging to class C in region K. So we will end here. I hope you learn something new, and we will continue in the next class. Thank you for joining.